Shit.
Y'all went to Sasha party this weekend?
Oh, yeah, Sasha?
Yeah.
That's my brother, baby mama.
Cool.
Child.
Uh-huh. 3.
You know that party was a mess, right?
I bet, ratchet.
Her mama came in.
Uh-huh.
Wow. Oh, crap, they gonna be talking.
Good morning, class. Today we're going to be discussing some introductory calculus.
Calculus. I'm not doing that.
Oh, I hate math.
I got a question. Excuse me, Miss Jones. How is this calculus going to help me in my future as a biology student?
Well, Bobby, in this equation, this function can be used in the biological field. For example, it can be used for modeling an enzyme reaction or population growth. N could be the nutrient concentration. F could be the growth rate function for bacteria. K max and Kn are positive constant parameters standing for maximum growth rate and the nutrient density at which the bacteria growth rate reaches K max divided by 2.
Okay, to better understand the Michaelis-Menten equation, I'm going to explain to you how we get there. So let's review the idea that if we keep the concentration of an enzyme constant, the really high substrate concentration will hit the maximum speed for the reaction, which we will call Vmax. I'll start by drawing up this sequence with the 3 different reactions. And I'll also write out the steady state equation where we have rates forming ES equal to rates taking away from ES. First thing we'll do is swap out the rates values for their rate constant. So rate 1 will be equal to K1 times E times S, and so on for the other 2. Next, I'll introduce a new idea and say that the total amount of enzyme available, which we will call ET, or E total, is equal to the free enzyme E plus S. Plus ES. Okay, using this equation, I'm going to rewrite the E on the left side of our equation as the total E minus ES, which would be equal to the E we had there before. And on the right side of the equation, I'm going to factor out the ES. Next, I'm going to expand the left side of the equation. Now what I'm going to do is divide both sides of the equation by K1. And on the right side, I'll put K1 with all the other rate constants. Now, since all these rate constants are constant values, I'm going to combine them into an expression of K minus 1 plus K2 over K1 as Km. Now I'm going to substitute Km into the equation and add ES times S on both sides. Next, I'm going to switch up the right and the left sides of the equations to clear it up. Also, I factored out the common term ES on the new left side. Now I'm going to divide both sides of the equation by Km plus S. So Km plus S moves to the right side of the equation. Now the speed of this whole process, which I'll call VO, is equal to the rate of formation of our product. Which is also equal to K2 ES. Using our equation over here, I'm going to multiply both sides of the equation by K2. Now, if VO equals V max, which is E total equals E S, then K2 E total equals V max. Okay, so then I'll sub in K2 ES. So then I'll sub in K2 ES for VO and K2 ET for V max. And I'll finally get our end equation, which is the Michaelis-Menten equation.
And how does this relate to chemistry?
The pH determination of an aqueous solution is used in analytical chemistry. Ca and Cb are the concentration of acid and base solutions. Va and Vb are the volumes. Kw and Ka represent the equilibrium constants for water and acid. H plus is hydrogen ion. pH is obtained as negative log hydrogen times hydrogen. This equation can be used for dilution as well. Calculus is used to show how an equation can grow or shrink, accumulate over time, when it reaches its highest and lowest point, how we use variables that are constantly changing, such as heat, motion, populations, and so on, and can find the patterns between equations.
Okay, well, I guess you're right.
Yeah, just hurry up and teach it. So.
Apparently we can
Well,
use it in
thanks,
life.
I guess.
Alright, so now that you know how it will benefit you, let's get into it.